Okay, so this lecture is about estimating natural frequencies using a method called the Rayleigh-ritz method. And this is in section 10.5 of Centuria. There's also, for example, there are many books of mechanical engineering about this, and one of them is this book by Mirovich called Principles and Techniques of Vibrations, and this is the sections that talks about this. So Mirovich's book goes over this in a lot more detail than Centuria does, and what we're using here is a very simple form of the Rayleigh-ritz method if you'd like to learn more about it. Mirovich's book is an excellent reference. So here's the idea. We know that with a lumped spring mass system, so we have the mass is concentrated at a point, and the spring has no mass, so all the stiffness is in the spring, but it has no mass. And so we know that the formula here is that the natural frequency is square root k over m. So what happens if, for example, we wanted to calculate the resonant frequency of a structure that looks like this, right? It's a real spring that actually has mass distributed over its entire structure, and there's no point mass, and so the only mass in this system is in the spring, and so how do we calculate this? So one example where this comes up is, for example, if we look at this comb drive resonators here, then this is one we've seen many times before. The natural frequency is square root k over, it's written here as MP, where MP is the mass of the proof mass here, or the mass of the moving plate. So that's all this stuff with the comb fingers and everything, that's all moving with a particular velocity. And then it says here plus 37% of the spring mass. Okay, so K is the spring constant that we calculated from the lecture and flexures. But where does this denominator come from? How do we get this factor of 0.3714? Well, I'll make an intuitive argument for this, is because the whole body of this thing is moving with some velocity x dot. And the springs, only the ends of the springs are moving at the same full velocity that this whole moving thing is. And if we followed this spring back to its base, obviously the anchor is not moving at all. And so the velocity of the spring is kind of linearly increasing as I come along the spring. This guy, let me just make this like hopefully more clear. All right, so this is x dot, that's the motion of the proof mass. It turns out that this little truss, this little bar here, it's actually moving at x dot over 2. It's moving at half the velocity. So the velocity along the spring is actually linearly increasing from 0 to 1/2 the velocity of the proof mass to actually the full velocity of the proof mass where it connects to the proof mass. And so the reason why the spring mass is weighted by this factor is that the spring is not moving at the full velocity. Okay, so we get some sense that the mass, the important part of mass, is going to be weighted by this velocity profile. And how do we come up with that? So here's the basic idea of Rayleigh-ritz. Here for a sort of a simple harmonic oscillator, so this doesn't really, it doesn't matter that this is a continuous system or something, but we could just think about it as being a spring. So if we had something that's moving, sorry, I need a spring here. We have a spring that's like this, and here's a mass, and we're imagining that this thing is moving with harmonic motion x of t. Okay, so that's what's shown over here. A is the amplitude of the motion, and we're moving as sine omega t. So what we called before, like the elastic strain energy, the elastic strain energy, WE here, at time t, well, it's 1/2 k times x squared, okay, 1/2 kx squared. And then the kinetic energy in the mass is 1/2 mv squared, okay, so this is 1/2 mv squared. That's equal to the kinetic energy, okay. And now here's a plot of the elastic strain energy, that's this red line here, and then the kinetic energy in the mass, and we can see that they are oscillating. One of them is sine squared, and the other one is cosine squared. But what happens is basically the energy is sloshing around, so it's transferred from, there's basically 0 potential energy here at T0, and all the energy is in the kinetic energy, and then it just transfers from one type of energy to the other. And then this is an example where there's no dissipation. So there's no damper here, there's no resistor. And so the energy is just constant, and it's just transferring from one form of energy to another. And so hopefully we can see that the maximum kinetic energy is equal to the maximum potential energy. And well, what is that? Well, that would be if we ignore the cosine squared and the sine squared, because those guys, their maximum value is 1. And so we can see that we get 1/2. So this WK is equal to WE says that 1/2 K A squared is equal to 1/2 M omega squared A squared. Okay, that's what we're saying here. Okay, and what we could do is, well, it turns out that some stuff drops out. Actually, the interesting thing is, and we'll see this later on, the amplitude of the motion doesn't matter. It turns out to be arbitrary because it appears in both of these energy terms. It appears squared. So this goes away, and then this factor of 1/2 goes away. And what we're left with is the usual familiar formula, which says that omega squared is equal to K over M. Okay, so if we equate the maximum kinetic energy to the maximum potential energy, I'll use a red color for this. Starting from that equation, we end up getting the usual solution for the natural frequency. Okay. So how do we actually apply this to a continuous structure? Well, what we need to do is we need to be able to evaluate. We know how to evaluate the elastic strain energy. Okay, so now we need to be able to evaluate the kinetic energy in this continuous body. Okay, so the idea is we have WE elastic strain energy. This was in lecture 11. Okay, so here what we're going to do is we're going to calculate WK, which is the kinetic energy in a continuous body. Okay. So how do we do this? Well, we start with if we look at this vibrating string or whatever it is, we could say that remember I called this thing U is the displacement, and it's got some displacement. It depends on the x-axis position, and it also depends on time. Okay, and so what we're going to do is we're going to say that, so x is this direction here, right? So x is the deflection of this thing at position at point x at time t. So we use separation of variables. We write u of x and t is equal to some u of x times another function, which in this case I'm going to call cosine omega t, like that. Okay, so we break it up into a spatial component. This part here turns out is the mode shape, and this is basically the time dependent. This part here expresses the time dependence of this thing. And so now, in terms of calculating kinetic energy, remember that what we want to do is for kinetic energy, we end up with this 1/2 m times x dot squared, and like it says in this thing here, masses are weighted by the square of their velocity amplitude. That's what it turns out to be. Masses are weighted by the square of their velocity amplitude. So let's figure out what the velocity is here based on this expression. So I'm going to write it as u dot is equal to, well, u of x, it's no dependence on time, and so we get omega sine omega t. And now remember that we only care about the maximum velocity amplitude as a function of time, okay? So maximized over time. We find that u dot is equal to omega times u of x. Okay, so that gets rid of this sine omega t. We want to find the maximum velocity over time at each point x. Okay, and so if you remember, the idea is we had kinetic energy is equal to 1/2 m x dot squared And this is the velocity at point x along the beam. So we should really be thinking about an infinitesimal mass an infinitesimal volume, and that one has, so maybe we'll call it like d wk is going to be equal to 1/2, and the mass of some infinitesimal volume is going to be equal to the density at that point times the cross-sectional area times dx. Okay, so that takes care of the 1/2 m part, and then I need u dot here. Okay, so for our continuous body, then the kinetic energy is found by integrating over the length of the beam from 0 to L 1/2 rho a times, sorry, this should be u dot squared here, omega squared u squared of x dx. Okay, so this is our expression for the kinetic energy of a continuous beam. Okay, and it may be that the mass density and the cross-sectional area could be varying as a function of x, right? So they may be, I could say it's like a of x and rho of x. I'm going to ignore that for now, just because it makes the writing a little bit simpler. And what I want you to notice is that the kinetic energy is basically we find it by integrating the mass times the cross-sectional area multiplied by the displacement squared, where u of x, remember, is the mode shape. Okay, so it's the displacement squared that's important for calculating the kinetic energy of this body. Okay, so what's the procedure? Well, we're going to we use the mode shape u of x to calculate WE. So WE is the elastic strain energy. So we use the vibration mode shape to calculate the elastic strain energy. This is exactly what we did in the last lecture. And we're going to equate that, WE, to WK, where WK is the kinetic energy integral that I put on the previous slide. So we end up, I'm not going to write what WE is because it's complicated, but WE is going to be equal to WK, which is equal to, turns out, 1/2 omega squared times the integral of rho a u squared. Sorry, that's not so obvious. It's a u squared of x dx. Okay, and then we can solve this for the resonant frequency. We get omega squared is equal to the elastic strain energy integral divided by 1/2 integral rho a u squared of x dx. Okay, this is the formula for the estimated natural frequency. Okay, and so we found the elastic strain energy by using the same techniques from the previous lecture, where our trial function now is the mode shape, and we can think about that as kind of like being the stiffness of this particular mode. And on the bottom here, we have what we can think about as the modal mass, which we find by multiplying the mass density times the volume by the square of the mode shape. Okay, so it's the displacement squared is the important thing in evaluating our modal mass of our device. So we can think about this as the modal stiffness. This is the modal mass for this particular vibration mode. Okay, and I'll finish in the next part.